Hello, Saurav. Good morning. How to fit a curve with empirical data points. Now, the question is very simple. It is exactly the same kind of question that comes when digital processing. For example, how do you convert an analog signal into a digital signal, for instance? Right? Yeah. You see, you're giving me an example from heart functioning of the heart. You could take an example from biology, you could take an example from physics, or you could take an example from image processing, for instance. Or take a continuous function. What do you mean by empirical data points? You sample the signal at a discrete set of points and you try to get an approximation for that. Just 1 minute, please. I'm getting a call. Hello? Hello? Yeah?
Have you received a package? I'm from the Revolver Club.
No, not yet. Actually, yesterday the gentleman came at 9 o'clock. I asked him to come today, actually.
Okay. What timing you have asked him to come?
He said he'll come before 1 o'clock.
Okay.
He has sent.
If you got the package, just let me know. Okay, via text or call, anything is okay.
Yeah. Because I will not be there. My colleague, somebody in the math office will collect it for me.
Okay.
Yeah, right. Your name?
Aksha. I'm Aksha.
Aksha, I'll just call you back after an hour because he said he'll come only at after 12:30.
Okay. Just let me know.
Sure. Certainly. Thank you very much. Yeah. So the point is, if you use the traditional Fourier analysis like sines and cosines, you will need a large number of terms so that the partial sums will give you a reasonable approximation to the signal. So you need to use different types of orthogonal systems, and that is exactly where wavelets come in. So the idea is to use wavelet analysis rather than classical Fourier analysis. You should look up Strichart's book, for example. Look at the book of Robert Strichart's, which I have several times referred to in the notes. There's also a book by Bracewell, Bracewell, Bracewell. You should look up the books by Bracewell and others. Have you written down the name? Hello, Saurav. Have you written down the names that I've given you just now? Robert Strichart's Guide to Fourier Transforms and Distributions, and Bracewell, Bracewell. Got it? Hello, Saurav. Can you type something and respond? Hello, Saurav. Can you hear me? Can you respond whether you got the names of those two references I've given you? Hello, Saurav. Are you there? Yeah. Did you get the names of those two books, those references? Bracewell and Strichart's. Robert Strichart's. Strichartz. Robert Strichart's. Okay. Any other questions, please? Any other questions, Saurav? Yeah. Anybody else is there in the among the audience? Any other questions? Okay. Any other questions? Anybody else out there? Anybody else? Any other participants? Okay. How do you find the course? Which institute are you from? What are you doing? Which institute are you from? Which institution are you from? Where are you doing your PhD? SRM Chennai, automation engineer. Okay. Welcome others. Any question? The fortunates. Any questions? Brown? Any questions you want to ask? Hello, Ansh Kaushik. How do you find the course? All of you, how are you finding the course? We are in the seventh week now. So some 35 capsules are done. I think we are in the chapter 6, I think. Chapter 5 or chapter 6 or something. How do you find the material? Anksh, Saurav, Fortunates, Brown, how do you find the material? Say something, ask something. Any questions, anybody? Anything in mathematics? No questions? All is clear? How do you find the course? Easy, difficult, interesting, boring? What is the well structured? Oh, thanks. That's interesting. The course is well structured because material in the first chapter will appear in the 8th chapter again. So you're working in partial differential equations. Somebody is working in partial differential equations. Although the material that I'm talking about is well known, this particular collage that you see, that is unusual. What is QM? Quantum mechanics. Quantum mechanics today uses a lot of ideas from Fourier analysis, because a Fourier transform it is what it does the job of taking the position operator and the momentum operator, exchanging the position operator and the momentum operator, writing the quantum mechanical analog of the simple harmonic oscillator gives you the Hermite equation and the analysis of the Hermite equation. Yes, Ansh, assignments are difficult, slightly difficult. The problem is the following. When I learned did my bachelor's in mathematics in one of the colleges in Mumbai, did a master's in Bombay University, and when I went for my PhD at Minnesota, I was doing a PhD in partial differential equations and analysis, and I found that there are many things in the bachelor's and master's level that I have missed out. There is a lot of mathematics that is now coming up in research. Take, for example, special functions. Special functions are coming back with a vengeance in mathematics. Yeah, this creating a playlist. Okay, so the point is all these videos will be available in a link, and these videos will be going serially. Lecture 1, lecture 2. So if you click on lecture 45, after lecture 45 completes, it will automatically start lecture 46. You can actually send me an email and I'll be happy to share the link with you. Practical examples of Fourier series. You can look up, for example, Churchill-Brown Fourier series and boundary value problems. There you will see large number of examples are worked out. Large number of examples. So the idea is we have avoided in this particular course doing numerous examples of a same kind, taking too many examples and working out all the gory details. We have avoided that. Rather, the emphasis is on covering a wide variety of things, touching upon concepts which are not emphasized much in specific books. If you look at Churchill-Brown's book, you will find a lot of computational stuff. Strichart's book is very good, but it touches upon many other things. It doesn't do the number theoretic aspects at all, for instance. Number theory books tend to get too deep into number theory. We don't want to be getting too deep into number theory. We want to see Fourier analysis in action and applications of celestial mechanics that is usually not touched upon in classical Fourier analysis books. So the idea of doing all these things is to bring about a certain synthesis of concepts from various parts of mathematics: ordinary differential equations, partial differential equations, complex analysis, functional analysis, celestial mechanics, ODEs, PDEs, etc. Brown, what does it mean to say position space, momentum space, or Fourier space? You see, in quantum mechanics, what exactly is quantum mechanics? There is this classical philosophy, the classical viewpoint, and the quantum view. So physical quantities which appear in classical mechanics, like position, momentum, energy, etc., they in the quantum picture are represented by operators on a Hilbert space. So they're called observables. So observables in physics are expressed in terms of operators, unbounded operators on a Hilbert space. And there's a dictionary. Position means multiplication by x. That's an unbounded operator. Momentum means 1 upon I dx. The total energy will correspond to some combination of these operators. So what is happening is that we got when you have a bunch of variables, some combination of positions and momentum, some function of these positions and momenta, that will correspond to some operator. And so you got this dictionary going from classical observables to the quantum mechanical analogs. And this process is called quantization. And the amount of Fourier analysis that is required is quite a lot, because if you take, for example, functions in the classical sense, how do you associate an observable? That is achieved using ideas of pseudo differential operators or Fourier integral operators and stuff. Okay. Anything else? Yeah, Deepak Sharma, write to me an email and I'll probably share the link with you. And these videos will appear in series. But I think this link was shared with all of you. If it is not shared, I'll probably share it with you, where these videos will appear in a serial order. And my suggestion is download the videos in your local area, because I do not know when these videos will be removed. We have no control over it. So just as soon as you go to open your browser and you see these videos, you just download them in your site. Any other questions, please? I think they are done. Okay, so if you don't have any other questions, should we stop? Are the time left to join this course? Oh, what is the value of modulus of gamma ix? Mod gamma ix squared is gamma ix into gamma minus ix. Multiply and divide by minus ix. Minus ix into gamma minus ix is gamma 1 minus ix. So numerator becomes gamma ix into gamma 1 minus ix. the denominator is minus ix. But gamma ix into gamma 1 minus ix is pi by sine pi ix. So the answer is pi by x hyperbolic sine pi x. And now you have to take the square root because you asked me for, Ansh asked me for the mod of gamma ix. So what is mod of gamma ix? Root pi by root mod sinh pi x. Sinh x, there's an x also in it. Root pi by x sinh pi x square root. Every function can be created by a Fourier series. Answer is yes and no. It depends upon what you mean by every well-behaved. If you have a Holder continuous function which is 2 pi periodic, its Fourier series will converge pointwise. If you don't have Holder continuity, if you just have continuity, the Fourier series will converge in the sense of Cesaro. If the function is in L2, the Fourier series will converge in the sense of L2 convergence. If it is very ugly, you can still ask for distributional convergence, and that will be the last part of this course. So a fairly general function, even functions which are very badly behaved, will admit a Fourier series expansion. The only problem is that Fourier series will converge in a very weak sense, namely in the sense of distributions. Om Shri, what is the question? What is the time left to join this course? That you'll have to look at the course website. I think the last date for, I think you'll have to look for the course website and do the online registration. Anything else, please? Keep asking questions, please. Next question, please. Keep asking. Roderick's formula in polar form. You will have to put x equal to, see, in Legendre polynomial, the x is cos phi. When you study the Fourier, when you study the hydrogen atom, the azimuthal quantum number comes from this x equal to cos phi, and then that cos phi satisfies the Roderick's formula. If you try to put x equal to cos phi in the Roderick's formula, it is going to become a very complicated expression. You can look up Whittaker. You can look at Edmund Whittaker's book. These expansions are given, like Jacobi. I think that expansion is due to Jacobi. What is the value of integral of sine kx upon x dx? It is pi by 2 if k is positive, and minus pi by 2 if k is negative. Brown, it is pi by 2 if k is positive and minus pi by 2 if k is negative. So it's pi by 2 times sine k. Of course, it is 0 if k is 0. Yes, for any value of k. If k is 0, it is 0. If k is positive, it is pi by 2. If k is negative, it is minus pi by 2. Okay. How to find the conversation of sin x by x? What does it mean? I don't understand conversation. What do you mean by that statement? Can you please reformulate the question? Ansh, what is the question again? I don't understand what you mean conversation of sin x upon x. Convolution. Convolution of sin x upon x with what? With itself? You mean sin x by x convolved with sin x by x? Is that what you're asking? It's a convolution with what? You give me two functions, no, for convolution. One of them is sin x by x, other one? Do you want to take the convolution with itself? Okay, so take the Fourier transform. Sin x by x convolved with sin x by x Fourier transform is a product of the two Fourier transforms. No? But what is the Fourier transform of sin x by x? One half the characteristic function, from -1, 1. So you're looking at the square of the characteristic function, but the square of the characteristic function is itself. So Fourier so you take the inverse Fourier transform. So what is sin x by x convolved with sin x by x? It is going to be pi times sin x by x. It's going to be pi times sin x by x. Yes, there's a compromise. If you have a very sharp signal, the Fourier transform will be dense, diffused. If you take a very diffused signal, the Fourier transform will be very highly localized. The Gaussian manages to obtain a good balance between the frequency domain and the time domain. You should look up Strichard's book and look up the Heisenberg's uncertainty principle, and that discussion centering around that. Any other questions, please? I'm very glad people are asking lots of questions. And these questions are really very unusual questions. I'm very, very glad people are really looking at the matter and really absorbing the matter, it appears to me. Very good. Okay, any other questions, please? Also, feel free to send me emails if you want to ask any other things, like if you want references, if you want to ask any doubts, feel free to send me, contact me by email, gopal.gauss@gmail.com. gopal.gauss@gmail.com. Please write down gopal.gauss@gmail.com. Send me an email and I'll be able to give you more. So you want to move on? You want to ask me further questions? If you don't have any further questions, we will stop it. If you have questions, please ask. Yeah. Anybody else? Anybody else has any questions, please? So feel free to send me an email, gopal.gauss@gmail.com. Okay. Mathematics of the Heisenberg Principle, Stitch Charts. Look at Stitch Charts' book. Fourier transforms, distributions, and Fourier transforms. The book has been cited in the slides several times. You'll see lots of citations of that. Thank you. Okay, so I think we'll close it here. We'll continue with next Wednesday, 11:30. Next Wednesday, we'll continue with 11:30. बता देना वो कल को